Yeah.
So I'm just gonna give you guys just a broad example. I'm just gonna give you guys a function is equal to, let's just say, x minus 3 times x plus 2 times x minus 5. So the sketching graphs, I believe, was 2.3 or 2.2.
2.3.
2.3?
Is this on the test?
No, I'm going to show you guys how to calculate the maximum mins of odd and even degree polynomial functions.
Yeah.
So for this specific example over here, where would our zeros be located? Sorry.
Positive 3. Negative 2. Positive 5. Sorry.
X is equal to negative 2, 3, and 5. Okay. What's the degree?
3.
Are you doing coefficients? Positive or negative?
Positive.
All right. So if it's a positive odd degree polynomial, what quadrant is it going from into?
3 to 1.
Okay. All right. So we're going to draw our axis. We have one at negative 2. We have one at 3. And we have one at 5. So we're going from quadrant 3 to quadrant 1. Because the order of each bracket is 1, the graph's just going to go straight through the x-intercepts. Okay, so we're going to go through here. All right, so as you can see, here we have some maxes and some minimums. Okay, so to calculate those maxes and mins, when we have a parabola and the two x-intercepts, how do we usually calculate the vertex given the two x-intercepts?
You get the two x intercepts, add them together, divide by 2.
Yeah. So you're doing the same thing with this, except you're going to do it depending on the number of turning points. So you're going to have to do it twice in this case. So here you're going to have a max, and here you're going to have a minimum. So the x-intercepts that we're going to use to find out what the max point is going to be negative 2 and 0, and 3 and 0. So we're going to find our max. So we're going to add the two x values and then divide by 2. So we're going to get negative 2 plus 3 divided by 2. And what does that give us? Negative 2 plus 3 divided by 2. Obviously, I'm going to draw this graph better, so that, because you know this is not a half. A half is supposed to be over here. So now that we know for a max that x is equal to 1/2, how do we find out the y value of that?
Don't we just plug the x?
Yeah, so we're going to plug in 1/2 for our function.
Wait, sir, why do we not know this?
Pardon?
Why do we have to know this?
Because there might be a question on your test that says find the maximum.
Wait, this unit?
No, for the thing you have on Tuesday.
Oh, okay.
Multiple choice is 1, weightings for the written part is 3. So it's, yeah, 3 times worth more than.
Well, I think I know what question that is.
Okay, so can someone simplify that for me? Oh, I see everyone's getting their calculator all at the same time.
Why? I guess I'll do it. Oh. Who's ready? You
I just needed to know if I was shivering because I'm like nervous. Hold up, what?
Jose,
What you got?
one pass.
Doesn't necessarily mean to me. You guys can tell
No, it has to be. Do the children.
why me.
Sir, would the question specify whether?
I'll tell you, if I'm telling you to graph and I say, look at the maximum and the mins, that's what you're going to do. You guys get 85 over 4 or something like that?
This isn't even talking.
Okay, so our max point is gonna be at 1 over 2 and 85 over 4, which makes sense because the function is increasing from negative infinity all the way to our vertex point at that point, okay? So 1 over 2 and 85 over 4, that's gonna be our max. Obviously, I'll give you numbers that give you full numbers. This I just made up off the top of my head. So that would be your max point. So if I draw this like I'm supposed to draw it, let's not ruin the blue line. So 85 over 4 is 21.5. So it's going to be somewhere over here. Okay, so that would be our max. 1 over 2 and 85 over 4. And then we would do the same thing with our minimum value. So for our min, we're going to use 3 and 0 and 5 and 0. So we have min is equal to 5 plus 3 divided by 2. And what is our x value going to give us? 4. And now we take that 4 and sub it into our function. So we get f of x is equal to 4 minus 3 is 1. 4 plus 2 is 6, and 4 minus 5 is negative 1. So what does it give us? Negative 6. And does that make sense? Okay, because it is decreasing up until that vertex. So again, I'm going to draw this more accurately. So we have our max value of this graph at 1/2 and 85 over 4, and our minimum value at 4 and negative 6. Okay? So I suggest you either, if you didn't write notes, look back at this later, because there will be a question where I specify to locate the max and the mins of the function. Okay? Don't worry, I made the numbers easy to work with. I don't think there's a fraction. Maybe it might be like 1/2, and that's probably it. All right, so I'm not going to get into the whole concept of local maximums and absolute maximums and mins.
Yes, I don't know what that is.
Okay, so local maxes and mins are only existent in odd degree polynomial functions because you have multiple turning points throughout the function. Okay? So I'm going to just add a new page. Okay, so local maxes and mins are with odd degree, okay? Only because if we look at this, right in all caps, you want to point across. So when we look at odd degree polynomial functions, okay, yes, we do have a maximum and a minimum, but is that the highest and lowest point that that graph reaches? No, because the left side keeps approaching negative infinity, so it's going to keep getting lower, 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 and the right side keeps approaching positive infinity. So these turning points over here are known as local maxes and mins, because those are the turning points of the graph. So this would be a local min.
And what's absolute?
I'll show you. That's for even degree.
Oh, okay. Oh, that makes more sense.
And you'll start to realize why it's called an absolute max for odd degree. I mean for even degree polynomial functions. So when it comes to even degree polynomial functions, you will have either or. Okay, you won't have both. You will have one or the other. So we'll look at absolute max and min.
Wait, sir, I remember there's a question in the textbook, something about this, but like I forgot. But it's like what type of question would you give us when you say like local or like absolute?
Oh, so I would say, does the function x to the 4 plus 3x squared minus x have a local maximum or minimum or an absolute maximum?
Maximum, like actual like rating or something for that?
You can, if it's factored, you can figure it out just by doing what we did previously with this example over here.
Yeah.
Just by adding the x-intercepts, summing it back into the function, and you'll find your maximum. So absolute max and min is only for even degree. So let's just take, so the end behaviors for a even degree polynomial either go to negative infinity or positive infinity, right? Depending on the coefficient. So we could have, let's just say a graph that looks like this, okay? What would these 2 points over here at the end be called? Is that the absolute lowest point the graph's gonna hit? Yes, so it's gonna be called a absolute minimum. Remember, absolute means that it is the lowest or the most highest points of the graph. And when you have an absolute minimum with a even degree polynomial function, you will have this. What do you think this would be called up here? Because it's not the highest point, so it would be a local max. Okay?
Oh,
Because it's not the highest point of the graph.
but I thought local was only odd degree.
So local max and local min are for odd degree. You will never have an absolute max or an absolute min for an odd degree function. But for even degree, when the leading coefficient is positive, you're gonna have absolute minimums and a local max. Okay? So when the polynomial leading coefficient is negative, what do you think you're gonna have?
The other way around.
It's the other way around. You're gonna have an absolute max and a local minimum. Okay? Because that turning point where it goes back up to the max is not going to be the lowest point of the graph, but it's going to be a minimum because it is a turning point at a minimum value. So an example of that would be the same graph, just opening downwards.
But if it's like a parabola or whatever, that's basically just that's basically just absolute minimum.
So as you can see here, this is just a sketch. We have a max here, and a max here. Which one's the absolute max? The furthest one to the left or the one on the right?
First to the left.
So remember when you're talking about an absolute of anything, it's like the highest or the lowest of the graph. Which is why that doesn't exist in odd degree polynomial functions, because the graph goes in opposite directions in either quadrant, okay? So one of them keeps getting lower, the other one keeps getting higher, so there's no real absolute max or absolute min for odd degrees. So is everyone good with the concept of absolute max, local mins and maxes? All right, so now we're going to move on to the lesson, which is solving polynomial equations. This unit isn't necessarily hard. We're using what we learned from Unit 1 in terms of sets and interval notation. And that's going to help us determine where the graph increases, decreases, where the turning points are, where the vertex is going to be. So all you're doing for polynomial equations is you're basically solving, putting everything to one side and making it equal to 0. That's all you're really doing for polynomial equations.
Oh, is this when we have to start doing quadratic and stuff like that?
Yeah. What do you mean by quadratics? Pardon?
Quadratic.
Yeah. If you need to use it, use it. If you can just factor using sum and product, then just use sum and product. So we're going to look at some definitions that we've learned. So we know a polynomial function is an equation in which one polynomial expression is set equal to another. So we've done this before. X to the 3 minus 5x squared is equal to 4x minus 3. The zero of a function we know is the x-intercepts. Okay, so these are known as the x-intercepts, which are known as the zeros, or what other word do we use instead of zeros or x-intercepts? Or roots. So the solutions or roots of a polynomial equation are the zeros of the corresponding function. Real roots of a polynomial function equation is px is equal to 0 correspond to the x-intercepts of the graph of the polynomial function p of x. So real roots are any real number. It can be a decimal, it can be a fraction. Yes.
So what is a real number and what is, like, I guess, an imaginary? Is that the contrast between the two?
So you know how we have square root of -5?
Yeah. You can't have a square, I mean, you can have a negative underneath.
That negative becomes an I.
An I?
It's an imaginary. You don't learn it in calc and in university. So you get the root of 5i. That's what an imaginary number is.
What's that word beside roots?
X-intercept? X/INT.
What is it?
It's another name for a zero.
For zeros. So yeah, it's called zeros. You can call it an x-intercept or
X-intercepts. It's supposed to mean
It's
Oh,
just
oh,
yeah,
I
it's just
got
an
it.
abbreviation. So yeah. So don't even worry about this.
That's
He's just tripping out right now. He's like, an I is introduced. What is this? So forget about that. Don't even worry about the I. Jose's just getting too ahead of himself. Yes, Joseph.
Is that I like the fancy I?
Yeah,
Oh.
yeah, but I just write it as a regular I. Okay, so don't worry about. So these, yes, they would be called imaginary roots. Okay, so there are imaginary roots, but I'm not even gonna get into that. So a polynomial function of degree n has a maximum number of n real roots of the corresponding equation. So if we have f of x is equal to 5x5 minus 3x4 plus 2x3 plus x squared minus 2x plus 1, how many x-intercepts would be the maximum for this? Or how many roots?
4. Oh, wait, 5.
5. So remember, roots has to do with the degree. Turning points is the degree minus 1.
Wait, sir, is a half a real number?
A half, yeah, x, so 2x minus 1, a half is a real number.
So like, if it's a, 3 over 2.
That's still a real
So
number.
like, it's a, so,
As long as the discriminant of your quadratic formula gives you a positive root, it is a real number.
But if it's a negative.
But if it's a negative root, it's not a real number.
It's imaginary.
It's an imaginary number. You guys can Google that on your spare time. So at most, that function I gave you has 5 roots. So now we're going to start solving a polynomial equation by factoring. So we want to fully factor the polynomial. We want to set each factor to 0 and solve. So what that means, that last part means, is we have to move everything to one side and make it equal to 0.
sir,
Yes.
what's it called?
So A, we have 4x squared is equal to 16. So because we have to move everything to one side and set the other side equal to 0, which side do you guys want to move?
16.
We're going to move 16 over, so it becomes
Is there like a
4x.
set rule, or like you can do it both ways?
You can do it both ways, but remember, it's easier if the order stays from greatest to smallest. So we have 4x squared minus 16x is equal to 0. What can we factor out first? 4x is equal to,
Oh gosh.
what is, if we factor out 4x, what does that give us?
X minus 4.
X minus 4 is equal to 0. So what are our roots for this equation? We get 4x is equal to 0, divide both sides by 4. We get x is equal to 0. Or if we set x minus 4 equal to 0, we move the 4 over, and x gives us 4.
Do we have to show that work, or is that like,
No.
like we can just do it?
I mean, you can. I'm not going to take marks off if you don't, but
No, because like what I just did an arrow and I was like X equals.
yeah, that's fine. The next one, we have 3x cubed minus 81x is equal to 0. So we don't have to move anything over because we already have our right side is equal to 0. But what can we factor out first before we can solve for what our zeros are?
3x.
X. So we get x squared minus 27 is equal to 0. So what would our roots be? Okay, so we get 3x is equal to 0, we get x is equal to 0, or what else do we do? So we do the same thing we did with this one. We set x squared minus 27 is equal to 0. We move the 27 over, then we do what with it? We take the square root, so we get x is equal to plus or minus the square root of 27. Now, if you remember your radicals from last year, how do you simplify that?
That's a good question.
Well, it's the power of like 1 over 2.
So, what two numbers can you multiply to get 27 and one has a perfect square root? 3 or 9. So x is equal to plus minus square root of 9 times square root of 3. What's the square root of 9?
So it's 3.
Yep.
Oh yeah. Makes sense.
Is the plus minus important?
And yes, Matthew, we did just factor it. It's not a difference of squares because 27 doesn't have a square root. So we just had to move the 27 over and then take the square root, and that would be our roots. Oh, now our next one, we get into an even longer polynomial equation. You're still going to be using methods from the last unit, so you might use synthetic division. Example, this one, and factor theorem. So we're going to look at x cubed minus 3x squared plus x plus 5. So what do we need to figure out first? What was the last thing we did, the last lesson? From unit 2.
Figure out what we can put to the x and make it.
So you have to take factors of 5. Okay, factors of 2 don't matter because it's just 1. So what are some factors of 5? Plus minus 1, plus and minus 5. So now you have a 1 in 4 shot of getting it right on the first try. So what number, when we plug it into the expression, gives us a 0?
It's -1.
-1. So we get f at -1 is equal to -1 cubed minus 3 times -1 squared plus -1 plus 5. So you get -1 minus 3 minus 1 plus 5, and that gives us 0.
So this was on the quiz, right?
Pardon?
This was on the quiz, right?
Not this exact same question.
No, but like this, like the example.
Yeah.
Yeah, I was like confused. I was like, oh, the entire time I was like, I thought the quiz was like on the first like 3 things or something.
Well, I mean, technically,
nah,
okay.
I mean, I still did it.
I know.
I'm just saying.
but the questions I gave you that involved remainder theorem and factor theorem was just giving you the easiest number possible, just plugging it in.
Oh,
To the equations. So we know that x plus 1 is a factor. So now that we know x plus 1 is a factor, what are we going to use now so that we can factor the rest of this polynomial equation? Synthetic, oh no, this is stuck. So we're going to use synthetic division. So we have our -1. Let's use the blue color. So -1, our coefficients are 1, -3, 1, and 5. Right, so as usual, we drop the 1. 1 times -1 gives us -1. So what we're left with now that we've done synthetic division is f of x is equal to, we have our factor x plus 1, and then we're left with x squared minus 4x plus 5. So what is the easiest way to check if that trinomial can be factored? What do we need to determine from the quadratic formula that can help us easily identify if this can be factorable? I mentioned it already. Starts with the D.
wait, you lost. What's the
So
question?
you know the quadratic formula? You know the square root portion of it?
Yeah.
So we need to calculate the discriminant. And if it's a negative number, it can't be factored because you can't have a negative square root. If it is a positive number, you can factor it, which means we'll have 2 roots or 1 root.
Wait, so discriminant is 4AC.
No, b squared minus 4ac.
Oh, right.
Everything under the.
It's
Everything under the roots.
It's a negative.
And we only do for that trinomial part.
Yeah, because can you factor that using sum and product?
No.
No. So use the discriminant when you can't factor using sum and product. So we're gonna use our discriminant, which is b squared minus 4ac.
We don't have to square root it.
Yeah,
Well, you don't have to, because if it's a negative number, you know it's a.
and it's a negative.
Yeah. So we have our b is -4. So we have -4 squared minus 4 times 1 times 5. Usually, the discriminant is negative when both a and c are positive numbers that are bigger than b. So we got 16 minus 20, which equals -4, which means you cannot factor.
Wait, what? Wait. Sir, why do we need to factor? Like, you said like to check that. Why would we need to factor?
Because we want to find out the roots of the function. That's why.
Oh, okay. So like, right now, the question is just factor.
Yeah.
So we would just leave it at that.
Mhm.
But if it's like find the roots, we gotta go more than that?
Well, because this is a negative discriminant, we can't go more than that. But if it was a positive discriminant, then we can factor it more.
Oh, okay.
But because we have a negative square root, we can't factor it anymore, so you just leave it like this. And what is our only real roots in this factored polynomial equation? Therefore, the only real
Oh, so like
root
we would have to do it like for this question as well, like if it just says solve by factor?
is x is equal to -1.
How do you know it's -1? Like for sure.
Because we use the factor theorem.
Okay, so why is that the only known?
Because we have a -4 as a discriminant, so you can't have a negative square root. So this is going to be the only x-intercept that the graph is going to pass.
So if like I was positive, like 4 was positive for
Yep. Then we would factor this even more.
okay.
So I'll show you what that graph looks like. Let me just go on Desmos. Desmos is pretty useful. So as you can see, let me just show the other class, because I can't leave them out. So as you can see for that question, it does in fact only pass through one x-intercept. So we're looking at the blue graph. It passes through -1 and 0, okay? And then it still has 2 turning points, and the imaginary roots are nowhere to be found.
So what's the point of like imaginary roots and such if they can't exactly have it on the graph?
So from my understanding, from what I remember, is just an imaginary root is where I think it corresponds to the turning points of the graph, or one of them. Because the square root of 5 would be what?
Good question. 2.2.
2.2.
Actually, that's 2.9.
Yeah. That's just usefulness. There you go.
Imaginary. Complex stuff. Electricity. Wires.
Yeah, let's not worry about that. I don't want to be seeing a bunch of eyes on this thing. So yeah, as you can see, this graph only has one root over here. And from the graph I graphed above it, even the red graph has one root, and it still has a degree of 3. right, so we have a couple more examples. So we have example D. We have 3x to the 3 plus x squared minus 12x minus 4. So are we going to use factor theorem, remainder theorem? We can factor by grouping. What do you guys want to do?
Or the P and Q thing.
Hmm?
The P and Q thing.
Okay, who says by grouping? Raise your hand.
That's
I love democracy.
3. Oh, Yusuf just fell into democracy.
Wait, isn't that the P and Q thing?
No, P and Q is factor theorem. Grouping is just you're taking these two and those two and factoring them out.
Yeah, you can do that.
And if you have the same brackets, then you can factor it properly.
But like at the same time, it does not affect the
P and Q, you can do factor theorem if you wanted to.
Okay.
It's just because we have this set up, we can try factoring by grouping. But if you want to use factor theorem, I'm not opposed to it. You can use it. So what's the common factor between 3x cubed and x squared?
X squared.
So we're going to get x squared. We're left with 3x plus 1, right? And then what can we factor out from negative 12x and negative 4?
Negative.
So we get negative 4. We get 3x plus 1. So because we have these two brackets that are the same, we are left with 3x plus 1 times x squared minus 4. Can we further factor this expression?
Yes.
So what are we going to factor?
X squared minus 4.
Because it's a difference of squares. So what would our two brackets look like?
X plus 2 and x minus 2.
Therefore, our roots are x is equal to, what are our roots?
Negative 1 over 3.
Okay.
Negative 2 and positive 2.
So you have 3 real roots in this example. All right, we're going to move on to question E. We have 2x cubed minus 3x squared minus 1 plus x is equal to 0. So what strategy can we use to factor this expression? We're going to use factor theorem, so the P and Q thing. So what are the factors of P?
Plus minus 1.
Plus minus 1. And what are my factors of Q?
P plus minus 2.
Yep. So plus minus 1 and plus minus 2. And P over Q?
1/2 plus and 1.
And 1. So again, you guys have a 1 in 4 chance of getting the right factor and making the whole expression equal to 0. So, did you figure it out?
No, but I have a question.
Yes.
What is the symbol you put beside P and Q and Q over Q?
It's an element symbol.
Oh.
So P is an element of. Wait, I thought it was
Oh,
a.
wait, is that what? I thought that was
Rectangle.
Oh, it's a notation that just that
It's like,
that Greek E is just element of. That's
it's
what
like
it
when
means.
we put
Like,
XCR, right? So to speak.
Yeah, it's the same thing as XCR.
Like X is the element. Well, that's how you do
Element of.
How's that?
Dios.
Doesn't even look good.
Hey man, this thing is not
trying.
fancy.
He's trying, guys. He's trying.
I mean, I've drawn some pretty damn good arrows in this class so far. Okay, that was probably one of my worst ones.
You go, Seth. You go.
So, what factor works that makes the whole expression equal to 0?
Hold on, Jose.
Calm down.
Uh-huh.
Yep.
That's
It is
so-
a half. So f at 1/2 is equal to 0. So now what's our next step? You have more steps.
The division.
Synthetic division. So 1/2. We have 2, -3, -1, and +1. Drop the 2, and then you're multiplying by 1/2, which gives us 1. -3 plus 1 gives us -2. -2 times 1/2 is just -1. Then you get -2, and then you get -1/2, and it gives us 0. What can I take out of this? What can I divide it by 2? So all we're left with is f of x is equal, because we took out the 2, is going to be 2 times 2x plus 1 times x squared from here, from 1/2. Because when you put it back in the bracket,
I know, but isn't it -1 because like?
oh yeah, I'm sorry, oops. 2x minus 1. Times x squared minus x minus 1.
Can you ever write x as x minus 1/2? Or does it always have to be like 2x1?
It has to be in this form. I mean, that's the cheap way of doing it, but I don't want it like that.
Like, I mean, is it technically right if you just did it?
It's technically not wrong, but just the form is horrendous.
Understandable.
Wait, so the only x-intercept
It's
is
not a legal.
Well, we don't know if it's the only one yet, right?
So that-
Can we factor x squared minus x minus 1? Can we use sum and product? So what do we have to figure out? So we need to figure out our discriminant, which is b squared minus 4ac. Our b is -1, -4 times 1 times -1. And what does our discriminant give us?
1. You know, right?
5.
5.
Most of my math is-
No, so we get 1 plus 4, which is 5. Okay, so that means we do have roots. So
Quadratic.
we just need to figure it out. Okay? So we have our quadratic formula, but luckily for us, because we did the
You
discriminants,
don't need to do.
you don't need to do a lot. So let's see if you guys remember the quadratic formula off by heart.
X, I'm sorry, yeah,
I
X
think it's
equals
b plus minus square root of b squared
minus 4ac over 2a.
Is it negative b?
Yes.
Yes.
Wait, so since
Well, they
it's
don't
back
count
to what we gotta do.
I know you have physics.
Physics lesson.
I'm not challenging you. I'm
Yes,
agreeing.
Yusuf, what's your question? You have a question?
So since it's factorable, now you have to go to find factors.
So negative b, so we have negative times -1, which is just 1. We have 1 plus square root of 5 divided by 2a, which is just 2. So what would our two roots be? So we get x is equal to 1 plus square root of 5 divided by 2. Or x is equal to 1 minus root 5 divided by 2.
And we just keep it like that?
You can leave it like that.
You don't have
Because
to calculate the exact value.
this is an exact.
I'm sorry, the approximate value.
No. If I ever say leave it into the exact value, you're leaving it like this. So, yes.
Why does it not like decimal?
Because they prefer fractions, to be honest. I don't know why they don't like decimals. Decimals are important when it comes to finances and math. No one's gonna say I have Well, people say I have $250,000, but they'd rather say I have $250,000. Just sounds more. Well, also, what sounds more to you guys, $250,000 or 250,000?
40 million.
Yeah, because you have the word million in there, right? People are just gonna say, oh, you're still in the thousands if I say I have 250,000. But if you say million, they're like, oh, you're 75% away from a million. So we have our two roots. We have x is equal to 1/2. X is equal to 1 plus root 5 over 2. And x is equal to 1 minus root 5 over 2. So those would be our three roots for this expression. You guys are reading ahead?
I'm talking.
So we want to select the strategy to solve the equation x to the 4 plus 3x squared is equal to -3. So what's our first step? What's the first thing that I told you guys we have to do?
You gotta move the -3 over.
Yep. So set aside equal to 0. So we want to move the -3 over, so we get x4 plus 3x squared plus 3 is equal to 0. So what would our next, I guess, strategy be?
I mean, I would do some in product.
You can't do sum in product. You have an x4.
Wait, it only works with x3?
Sum in product only works with x squared, but you can get to x squared if you have a specific let statement.
Well, wait. Wait,
Are we gonna do that?
can't you just like do it though? Because like, it
Can
won't
you
be
do the
like
left
x
statement?
squared, and then like 3.
Oh, no. So remember when I think it was last unit or the unit before with our let statements, you can, this is where, if you take math in university, let statements are like your best friend, just to simplify
So
everything.
can't you just say let x to the power 4 equal like, sorry, no, actually you explain it. I don't know.
Does anyone want to take a stab at what my let statement should be? What's our lowest degree, or what's our lowest degree here? Okay, so let's pick a variable.
B.
Let B.
So generic.
So generic.
So cute.
I mean, why didn't you pick A? It comes before B.
Now we have to choose C, James.
So let's just say let A equal
Let's what? Let A equal.
Wait, what are we doing?
So we want to use sum in product, but the only way we can use sum in product is to somehow get this down to x squared.
Right.
And we can do that through a let statement. Okay?
Oh,
Because let statements allow us to sub in a value temporarily for these variables.
One question, didn't you just have to use like P and Q?
You can,
Okay, just wanted to.
but look at the degrees.
Yeah.
They're all positive, right? Or they're all even. Are you ever gonna get it equal to 0?
yes?
So we're trying to find out, right?
Wait, what?
can't.
I'm lost.
If you have a negative number and it's to a even degree exponent, it's always gonna throw you back a positive number.
Right.
This is not and the fact that the constant isn't even a negative number, you're always gonna get something bigger than 3. Right? So even if I put, say, x is equal to -2, I'm still gonna get -2 to the power 4, which is 16, already at a positive number. So it's never gonna actually be 0.
Wait, so you can't use Q and P?
Nope, because you're never gonna hit 0. Because of the even degree polynomials and the fact that this 3 is positive, it's gonna be impossible to hit 0.
Okay.
And I'll even-
That rule, yeah.
Yeah, and I'll show you on Desmos that this graph is never gonna hit 0. So we're gonna let A equal x squared.
Think about it. Something like squared would like have that.
This doesn't have x squared though.
Yeah. Can you like still do it? And then like flip it as like a.
That seems illegal.
No, because whatever you do if you divide by x here, you have to divide by x on that side. So remember, whatever you do to the left side, you have to do to the right side.
Wait, sir, Is it only because the constant is positive? Or is it because like
It's because the constant's positive and because the exponents are all even exponents.
okay.
Okay? So they will never be less than 0. Unless you have 0. So we're going to let a equal x squared. So we have a to the power of 2 plus 3a plus 3. So now, Yusuf, can we use sum and product now?
Yes.
Okay. So we have our a squared plus 3a.
Wait, what did we just do?
So we let a equal to x squared, right?
Yeah.
So when we do x to the 4 divided by x squared, what are we left with? So we're just left with a to the power of 2. Okay? So, and then this just plugs into x, so we're left with 3a, and then the 3 is just left by itself.
Oh, okay.
Makes sense.
You're gonna be like, sir, you made me do all this work just to figure out there are no real roots.
What? Wait, so that's how it is? That's how we ended?
We're not gonna end it like that, we just have to prove that there's no real roots.
Oh.
So we're gonna use our discriminant, so b squared minus 4ac. Our b is 3. And our c is 3. So what's 3 to the power of 2?
9.
9 minus 12, which gives us negative 3. So does that mean we have any real roots? Pay attention to this because this might be similar. I might be asking a similar question
Wait, sir.
on the assignment.
Now we could do sum and product.
Yeah, but because the discriminant is negative, means our square root is negative, so we can't have a root at all. And I'll show you why. I'll show you what the graph looks like, and you'll be like, okay, I see why it doesn't have any x-intercept.
I know, but I'm just confused now. So like every time we like you say factor something, even if it has sum and product, we gotta do discriminant first.
Discriminant. If you can't do sum and product, then do the discriminants.
But we can't do sum and product.
No, you can't.
That's what we.
Because our product is 3 and our sum is 3. So even if we do 3 times 1, that gives us 3, but if we add them together, it gives us 4.
Oh, okay.
When do we not find this?
When do we not? If you can do sum and product, or if you have a difference of squares. So no real roots. Okay, and why do we have no real roots? Let's see what you guys can come up with. Cohort A and C, you guys can answer this question too. Why do we have no real roots in this question? Okay. But what else? I'm talking about this expression in general. Based off just looking at the polynomial expression, why do we not have any roots? Joseph.
Because no matter what number you plug into it, it will not be 0.
Yeah.
Oh, that's what you said.
And what do they say about the exponents?
Even.
Yep. The exponents are all even. And one last thing. What is our y-intercept? That's going to determine this too. Someone said it's 3. Okay. So if I roughly sketch this graph, okay, it is going to have how many turning points? Three. So let's say 1, 2, 3.
Wait, how do we know it's oh yeah, that's
4 minus 1. So I'm gonna type this in on Desmos, and you guys, it might look like this, it might not. If I'm right, then I'm a genius. But if I'm wrong, then whatever, it's fine. I'll take the L on this one. So let's go to Desmos. So let's add another graph. So we said y is equal to x to the 4. Any bets on if who wants to bet if I'm right on this? Is my sketch gonna look like what I drew? Or is this sketch gonna look like what I drew?
I'm gonna say no.
No? Okay.
I'm gonna say yes. I'm gonna take it.
To be honest, I didn't even plug this in before class, so I didn't cheat. So I promise.
That's
Yes, sir.
what he stays.
I turned on my computer at 8 o'clock and then went to my workroom until
Okay.
you guys came.
I'll say
I'll say
Oh no, I drew it way wrong.
Okay.
Yeah.
Wait, so what do I do?
Delete the other two that way to clear.
Just look at the green one.
Okay.
So as you can see, we have our y-intercept at 0 and 3. And because our discriminant was negative, we have no real x-intercepts. So
For the turning point.
Yeah.
just here.
Oh.
So
That's like the.
you can sketch it. So
Yeah.
when we sketch it, at most it can have 3. So it can look like that, what I drew, depending on certain conditions.
What are
But,
the conditions? What are the conditions?
well, it depends on how I factor it and if it's factorable or not. Okay?
But we
Uh,
said it's not fair.
It's not factorable, okay? So I screwed up my sketch, so it is what it is. But generally, x4 looks like a big U anyways. So this makes more sense than what I drew.
So the maximum would be 3.
Minimum.
The minimum.
Because it's a even degree polynomial opening up.
So it's absolute.
Absolute minimum.
Okay.
I'm talking about like the maximum number of turning points.
Oh, the maximum number would be 3. The minimum number of turning points on an even degree polynomial is always going to be 1.
Because of the parent function.
Yeah.
Yeah, that's what I don't get. In the textbook's like even is 1 and then odd is 0, but I don't get it.
So let's just take x squared, okay? I'm not even presenting this to these guys. Sorry, guys. I'll present it now.
That's awkward.
Yeah.
And they're all like waiting.
So the green graph, as you can see, for our function, it doesn't actually ever hit 0. So we therefore have a absolute minimum. And for, like I was saying, for even degree polynomial functions, the minimum number of turning points is 1 because of the parent function x squared only has 1 turning point. Right? Because x squared just has the simple parabola and it has that minimum value, and that's the only turning point it has.
Okay.
For odd degree polynomial functions, do we count that bend as a turning point? No. And x to the power of 3, so I'm going to type it out here. This bend over here, Yusuf, this purple one over here, if I zoom in, this does not count as a turning point.
Okay.
So the reason why odd degree polynomial functions can have a minimum number of 0 turning points is because of the parent function y is equal to x cubed. Because this doesn't count as a turning point.
So like basically 3 is 0.
Yep.
Okay.
So max is n minus 1. Minimum depends on the parent function.
So if it's like x like 7.
Okay, the maximum number would be 6, and the minimum would be 0. 0. So you said x to the 7, right?
Yeah.
Yeah, so
But wouldn't it be
maximum,
like
yeah.
7 minus 3, so max is 4 and then all that.
Max turning points is always n, the exponent, minus 1.
Okay.
So that's the max. The minimum number of turning points depends on the parent function.
No, I mean like I'm pretty sure this question was because I remember there was like a dash. It wasn't like max or min. It was just like it can be 0 to like 3 or 0 to like 4.
The number of turning points?
Yeah.
Yeah, so the minimum can be 0, and if your exponent was, let's say, 7, it can be 0 to 6, up to 6 turning points.
All right. Thank you.
You're welcome. So remember that example we just did, there might be something on the assignments concerning that.
Wait, so are we still on unit 3 or 2 or what?
We're on unit 3 right now.
So the new one?
Yeah.
Okay. Well, yeah, $7. Not bad.
It's a lot of paper for $7.
Yeah. Good call.
How many pages?
I spent like 20 pages of
That's a lot.
staples, like 5, 7 pages.
So guys, we're almost done. When solving a polynomial equation using technology, we'll just use Desmos, okay? If you ever want to check your work to see if you factored it correctly and your x-intercepts are correct, use the Desmos application.
Can you explain like where the
Maybe one,
effects
bro.
are
I need to exaggerate more.
Six.
What?
Like a 25%.
First
No, bro, that's stupid. Annotations thing. I got a 45 on that.
I got 25%. What are you talking about?
Bro.
25%. I swear before it culminated with my last test, I had
Wait,
like
the
7
annotations?
You know my son
Yeah.
would take up to 25%.
the fry tests. Bro, it's
Yeah.
so bad.
Nah, those
You guys got tested on.
So I can draw like that, okay, guys? So this would be the maximum number of turning points. You have 1, 2, and that could be a possible way to draw it. But the minimum way would be like we saw in Desmos. This would be max turning points. And then the minimum would be what you saw on Desmos, which is just a big U, like the parent function x4. Oh, so in order of 2, remember, in order of 2, when that comes up, that means that the graph bounces at that point. So that's just all an order of 2 means. So that goes back to one of the lessons in Unit 2, where an order of 1 goes straight through, an order of 2 bounces or creates a parabola of some sort, and the order of 3 makes a bend like x cubed.
When do you have to buy a graph?
Never.
You know?
We're not allowed to use it.
They don't need one for university. They don't make you use calculators in university.
What do they do? What?
They don't make you, but like,
Actually.
You gotta use your head.
Wait, actually,
Out of all my undergrad, I'd probably use a calculator like
Twice.
not even, yeah.
What?
was
Is it because it's just mental math or?
It's because they give you easy numbers and most of it's just like, prove me this is true.
oh,
And you can't use examples because you would have to use a crap load of examples to prove your point. So just using like other theories and just other equations to prove your point is better than using like 20 examples.
Okay. So what is the point of a graph?
There's no point of it.
So they're just.
It's just an activity for grade 9s to use in grade 9 math. That's all it is for.
I'd say-
So the next example, we're gonna solve for the equation 3x3 minus x plus 6 using a graphing calculator. So this I already did for you guys. So we're gonna do it on, I'm gonna share the screen.
Oh, was it the red one?
Yeah, it's the first one I did. So it is going to be the red one. So I'm gonna exit.
we already used
So for example 3, what is the only, how many roots are there?
One.
One real root, which is or approximately negative 1.318, okay? Which means that when we factor this out, or when we're factoring it, we're unable to factor it further when we bring this down. When we sub in negative 1/3 or negative 1.348 into x, it gives us 0. But because we have a bunch of decimals after that, we can't really solve for the other real roots.
So we would use P and Q for this, right?
Yeah, you can. You can use P and Q. But like I said, because it gives you this weird number, it's gonna be hard to determine it just by guessing or by using P and Q.
Oh, so then what would you use?
This one, because of the specific number, I would just say use a graphing calculator.
But how would you tell? It's not like-
Yeah.
Oh, I would tell you guys on the question. I'm gonna give you guys numbers that work. I'm never gonna give you.
okay.
I'm never gonna give you like 2.967431 as a root.
So what else do you do like after this? You graph it?
Just graph it, identify the y-intercept and the x-intercept. So for y equals x3, at most, how many roots is it supposed to have?
Most?
At most, 3. Okay, based off this graph, how many roots do we have? 1, right? Because of the parent function. X3 has a minimum 1 root.
Sir, I don't really know how to draw this bed. Do you care?
As long as I can see a change in direction, it's fine, okay?
Can I just like label it like that?
No, you're not gonna draw me a straight line and then label a bend at 0, 0. And last but not least, take a 10-minute break, and I'll do this last example after the break. It's gonna take me more than 3 minutes.
There's like acceleration.
So cohort A and C, you guys can come back at 9:50. Matthew, hopefully I answered your question.